Good evening and welcome to The Sleepy Scientist, a quiet corner of the universe where curiosity drifts at half speed and the day's noise finally fades away. Whether you're lying in bed, watching soft light play across the ceiling, or letting the stars outside your window keep you company, this video is meant to slow your thoughts, steady your breathing, and remind you that science, too, can be soothing. Tonight we're exploring the elemental future, a calm journey through the building blocks of tomorrow. From starlight to circuit boards, from deep oceans to distant planets, we'll follow the story of matter itself as it continues to evolve in human hands. Before we begin, I'd love to know where in the world you're watching from. It's always wonderful seeing these quiet journeys span so many corners of the globe. And if you enjoy gentle explorations of science, please consider leaving a like and subscribing. It helps this sleepy corner of the internet reach more dreamers. To those already subscribed, thank you sincerely. And do tap the little notification bell so you won't miss the next bedtime voyage through the cosmos of ideas. Hopefully this video won't be too interesting and keep you awake, but if it does, at least you'll drift off with a head full of atoms and a heart full of wonder. So, as the night deepens and the world grows still, have you ever wondered what will happen to the elements themselves, long after us, when the earth grows quiet and the stars continue their work? The elements are eternal, yet their stories are never still. Every breath, every beam of sunlight, every flicker of electricity around you is a conversation between ancient atoms, carbon whispering to oxygen, silicon humming beneath your fingertips, iron sleeping in your blood. For billions of years, these same particles have danced through stars, oceans, and living things, rearranging themselves into the ever-changing tapestry of the world. Tonight, that dance takes a new step. The human age has become an elemental age, one in which we no longer merely use matter, but begin to design it. Chemists and physicists now craft new materials with atomic precision, searching for lighter batteries, cleaner fuels, safer alloys, and gentler ways to draw what we need from the earth. The phrase "the elemental future" means more than new elements on a periodic table. It's about how humanity's understanding of matter, from hydrogen to the heavier synthetic atoms, is reshaping the technologies that will define tomorrow. It's about what happens when we take nature's timeless ingredients and write new recipes for survival, comfort, and hope. Yet even as our reach extends beyond Earth, the origin of every future invention remains cosmic. The metal in a spacecraft or the lithium in a battery once burned in a star. The gold in a wedding ring was born in the collision of neutron stars before our sun even existed. The story of tomorrow's chemistry begins in the silence of distant light. So as you settle deeper into rest, this journey will drift from the hearts of dying suns to the quiet hum of modern laboratories, tracing how the same atoms that shape the past will continue to shape the future. And perhaps somewhere along the way, you'll find a new appreciation for the patient beauty of matter, the stardust that not only made you, but still waits to see what you'll make next. In the quiet beginning, before planets, before oceans, before even the idea of time as we know it, the universe was almost entirely made of hydrogen and helium. Two simple gases drifting through a newborn cosmos, light and weightless, yet destined to become everything. These were the universe's first ingredients, the simplest atoms, born from the cooling afterglow of the Big Bang, floating aimlessly until gravity found them. And gravity, as always, was patient. Slowly, invisibly, it gathered those atoms into clouds. The clouds thickened, pressed inward, and began to heat until they ignited in nuclear fire. In that moment, the first stars flickered into existence. colossal furnaces where light itself became matter's sculptor. Inside each star, the simplest reaction in nature took place. Hydrogen fused into helium. It doesn't sound dramatic, but this quiet conversion released enough energy to keep a sun shining for billions of years. Stars are engines powered by unity, separate atoms merging into something new, releasing energy and giving light to the universe. Over time, those same reactions continued their subtle transformations, stacking atoms together step by step. Helium became carbon, carbon became oxygen, and oxygen, through long chains of fusion, built elements all the way up to iron. But iron marked a limit, the cosmic full stop in a sentence of creation. Fusing lighter atoms releases energy, but fusing iron consumes it. So, when a massive star's core fills with iron, its engine sputters out. The outward pressure that once held gravity at bay vanishes, and the star collapses under its own immense weight. In an instant its layers crash inward, rebound, and explode outward with more power than anything the human mind can truly imagine. That explosion is called a supernova, a brief brilliant death that seeds the universe with new material. For a few shining weeks, a single supernova can outshine an entire galaxy. It's in those moments that nature performs its most complex trick, making the heavy elements. Gold, platinum, uranium, and dozens of others come into being only when atoms are squeezed and struck by neutrons faster than they can fall apart. A process known as the rapid neutron capture process, or simply the R process. You could think of it as atomic embroidery under impossible pressure. In those milliseconds of chaos, nuclei capture neutrons one after another, growing heavier and more intricate until they can't hold together anymore and decay into stable, precious metals. Each gold ring, each platinum electrode, each uranium atom used in a reactor today carries the memory of that brief, furious moment, when gravity's collapse turned into creation's burst. For years, scientists believed supernovae were the sole forges of such heavy elements. But in 2017, telescopes detected something even rarer: the light from two neutron stars colliding. When these dense remnants of exploded stars spiral together and merge, they produce gravitational waves and a cascade of new elements. The glow of that event matched predictions perfectly, confirmation that some of the universe's heaviest treasures are minted not in dying stars but in their final collisions. Somewhere out there, in the aftermath of those cosmic impacts, new gold and platinum are being born right now. It's strange to think about. Every circuit in a smartphone, every spark in a battery, every trace of gold that connects signals across a microchip once drifted through interstellar space. The material in your watch, your wedding ring, even in your blood's iron, was shaped in stars that lived and died long before the sun was born. When you hold anything metallic, you are, in a small but literal sense, touching the remnants of stellar fire. Stars are nature's great recyclers. They burn, collapse, scatter, and start again. Their ashes drift through galaxies, collect into nebulae, and eventually become new stars, new planets, and perhaps new forms of life. Every generation of stars enriches the universe a little more, adding new letters to the cosmic alphabet of elements. Over billions of years, that alphabet became complex enough to write oceans, mountains, and mines. Even the calm light of our own sun is part of this endless rhythm. Deep within its heart, hydrogen still fuses quietly into helium, producing the energy that warms Earth and powers photosynthesis, weather, and all the intricate chemistry of life. Every sunrise is the echo of a fusion reaction happening trillions upon trillions of times per second. It's hard to call that ordinary, and yet, for all their brilliance, even stars can't go on forever. The universe's supply of easily fusible hydrogen is finite, and with each generation of stars a little more becomes locked away in heavier forms. Cosmic creation is slowing down, not stopping, but stretching its rhythm over longer and longer timescales. Someday, far beyond human comprehension, star formation will fade, and the cosmos will grow cold and still. But until then, stars remain the foundries of possibility. They turn simplicity into diversity, light into substance, and chaos into structure. From the tiniest hydrogen atom to the heaviest uranium nucleus, every element follows the same principle. Under the right conditions, unity creates energy, and energy creates everything else. It's humbling to realize that our story, human, planetary, technological, is just a continuation of that process. We've inherited a universe already rich with materials, already mixed and tempered by cosmic hands. Every innovation, every piece of technology, every bright idea depends on ancient explosions that happened billions of years ago. In a way, progress itself is a collaboration across time. Stars begin the experiment, and humans carry it forward. The periodic table we know is less a chart of elements than a family tree. At its roots lie those first simple gases. At its branches the heavy metals of supernovae and neutron collisions. And perched at the edge of that tree, curious and careful, stands a species capable of taking what the stars made and imagining what comes next. Every innovation begins with an explosion that happened eons ago. Every idea rests on starlight turned solid. As the cosmos slows its own creation, humanity steps in, not to replace it, but to continue the quiet work of turning the old into the new. The stars have done their part. Now the elements are ours to understand, to reshape and to use wisely, as the universe once used them, with patience and with purpose. Beyond uranium, the familiar order of the periodic table begins to tremble. The neat coloured boxes that chart the world's elements stretch into unfamiliar territory, where atoms are no longer stable companions of matter, but fleeting visitors that flicker into existence for mere moments before vanishing again. Here lies the realm of the super-heavy elements, the outer edge of the periodic table, and one of the most challenging frontiers in science. These super-heavy elements do not occur naturally on Earth in any measurable quantity. They are born instead in particle accelerators, massive machines that hurl atomic nuclei together at extraordinary speeds. The goal is to make them merge, to momentarily create something heavier than nature usually allows. Imagine two atomic nuclei, each positively charged and fiercely resistant to fusion, being forced together by a storm of kinetic energy. Most bounce apart instantly, but occasionally against the odds, they fuse for a heartbeat of time, forming a brand new atom that has never existed before. The process is both elegant and absurdly difficult. To make even a handful of atoms, scientists fire trillions of projectiles every second, for weeks or months on end, and then search through vast data for signs of success. Detecting a new element is like finding a single glittering grain in a desert of sand, knowing it will disappear before you can hold it. Each successful fusion event is celebrated not because it yields usable material, it does not, but because it expands the boundaries of what is known to be possible. The first step into this mysterious territory began in the middle of the 20th century, when scientists realized they could synthesize elements heavier than uranium by adding neutrons or protons to existing nuclei. Plutonium, americium, curium. These early transuranium elements extended the periodic table beyond nature's limit. But as each new element was discovered, their lifetime shrank dramatically. Nuclei grew unstable, decaying within seconds, then milliseconds, then even less. It seemed the table might soon end in chaos. Yet physicists suspected there was more to the story. The atomic nucleus, though unimaginably small, follows patterns of stability. Certain numbers of protons and neutrons, called magic numbers, create unusually durable configurations, much like closed shells in atomic orbitals. If one could reach a nucleus with the right balance of these numbers, perhaps even at very high atomic weights, it might last longer than expected. This hypothetical zone became known as the Island of Stability, a poetic name for a region of the periodic table where super-heavy atoms could live long enough to reveal their chemistry. Reaching that island has proven tricky. The path runs through a sea of instability, where most nuclei decay almost instantly by ejecting particles or splitting apart. But every new experiment edges closer. Elements with atomic numbers from 104 to 118, Rutherfordium through oganesson, have been synthesized, each representing a fragile stepping stone across that sea. Most exist for less than a fraction of a second, yet their brief lives confirm the periodic table's remarkable predictive power. Each new element demands creativity. Scientists choose target nuclei and projectiles based on how their proton and neutron counts might combine, then use immense accelerators to collide them. At places like Dubna in Russia, Darmstadt in Germany, and Berkeley in the United States, researchers work in quiet rooms shielded by thick walls of lead and concrete, waiting for the rare signature of a successful fusion event, often just one atom in an entire week of effort. When one of these atoms forms, it decays almost immediately, releasing a cascade of radiation that can be traced. By analyzing those decay chains, scientists confirm the atom's identity. It is painstaking detective work, but each confirmed discovery earns its own box on the periodic table, and occasionally a new name. Many of the most recent elements, nihonium, moscovium, tennessine, and oganesson, carry names honoring the regions or laboratories that helped find them, a subtle reminder that discovery is as much about human persistence as it is about physics. Super-heavy elements sit at the edge of what the nuclear force can hold together. Their immense nuclei bulge and distort, often described as pear-shaped or even teardrop-like under the strain of their own charge. These strange geometries create new kinds of behavior. Theoretical chemists predict that electrons moving near such dense nuclei experience extreme relativistic effects, traveling so close to the speed of light that their mass effectively increases. This changes how they orbit, how they bond, and perhaps even how they shine. In some of these atoms, the usual rules of the periodic table begin to blur. For instance, oganesson, element 118, sits at the end of the noble gases. On paper, it should behave like helium or neon, chemically inert and gaseous, but simulations suggest it might instead be a solid under normal conditions, because its electrons are so heavily influenced by relativity that they cluster closer to the nucleus than expected. If scientists could ever make enough oganesson to see, it might surprise us all by refusing to float away. This is what makes the super-heavy frontier so mesmerizing. It's less about producing material we can use, and more about glimpsing how matter behaves when pushed beyond familiar limits. These atoms exist for timescales too short for a human blink. Yet in that blink, they whisper clues about the structure of reality itself. Of course, the practical uses are non-existent. You'll never find furniture made of element 117, nor a necklace forged from element 115. Their lifetimes are far too short, their production far too expensive, and their radioactivity far too intense. They are terrible building materials, but wonderful thought experiments. Each fleeting atom is a conversation between imagination and the universe, a brief exchange in which nature admits, yes, that too can exist, but only for a moment. Still, from these brief existences come vast insights. By observing their decay patterns, scientists refine nuclear models, improve our understanding of the forces binding matter, and test the limits of relativity and quantum mechanics in one of their most extreme forms. Even a single confirmed event can alter the shape of theory, like a faint footprint revealing where stability might one day be found. The pursuit itself carries a quiet beauty. Researchers spend years tuning equipment, calculating cross-sections, and running endless simulations, all for a result that might last less than the flicker of a thought. There's something deeply human about that, chasing a glimpse of order at the edge of chaos. And perhaps that's the real meaning of the super heavy quest. It reminds us that curiosity doesn't depend on utility. No one builds an element like tennessine for profit. It exists because someone, somewhere, wanted to know if the periodic table truly has an end. Every tiny success extends humanity's map of matter, proving that even in a universe 14 billion years old, there are still corners waiting to be explored. When we look at the bottom row of the periodic table, crowded with names that didn't exist a century ago, we're seeing more than chemical progress. We're seeing imagination etched into atomic form. Beyond uranium, the familiar pattern dissolves, but so does any notion of limitation. Each box, no matter how brief its life, stands for a question answered, and countless more waiting. Curiosity itself, it seems, is elemental. It fuses together patience, precision, and wonder into something that, for all its fragility, still glows brightly. A reminder that discovery, like the stars, never really stops. Every modern civilization rests on a quiet foundation of elements, not the poetic kind, though they're poetic enough, but literal atoms arranged into metals, magnets, and microchips. They power phones, vehicles, wind turbines, and satellites. Yet most people rarely stop to wonder where they come from, or how fragile their supply can be. The term critical material describes this hidden tension. When an element is both essential to the economy and at risk of running short, it becomes critical. It's chemistry's way of saying, handle with care. Criticality isn't about rarity alone. Some scarce elements, like gold, are precious but not critical. They have substitutes and recycling networks. Others, like lithium or neodymium, are plentiful enough in theory but difficult to extract, refine, or distribute evenly. If a single country controls most of the supply, or if mining depends on delicate ecosystems, risk rises sharply. A material becomes critical when a shortage could slow industries or reshape economies before we can adapt. A handful of elements dominate today's watch list. Lithium, the lightest metal, underpins the global shift toward electric mobility. Cobalt adds stability and safety to many battery chemistries. Nickel enhances energy density, giving batteries longer ranges. Indium, almost invisible to consumers, coats phone and television screens with transparent conductivity. Then there are neodymium and dysprosium, the rare earth elements that make powerful permanent magnets possible, driving everything from electric motors to wind turbine generators to the tiny speakers in headphones. Each of these elements tells a story about modern dependence. Take lithium. Its name comes from the Greek word for stone, and it's found everywhere, from salt flats to seawater. But economically viable sources are rare, concentrated in specific brines and minerals scattered across South America, Australia, and parts of China. Demand for lithium compounds has grown so quickly that entire extraction industries have appeared almost overnight, straining both logistics and landscapes. Cobalt has its own complications. Much of it is mined in a handful of countries, often by small operations with limited oversight. Nickel, too, depends on a few regions, where refining capacity determines global prices more than geology does. This geographic concentration creates vulnerabilities. Supply disruptions can ripple through multiple sectors at once, from electronics to transportation. In some ways, materials have become the new geopolitics, quiet but powerful. Yet the tone need not be alarmist. It's not that we're running out of these elements. Rather, the challenge lies in managing them wisely, diversifying sources, and finding creative alternatives. Materials scientists are by nature inventive. When faced with scarcity, they design around it. Substitution has become both art and science. The search for new compositions that deliver the same performance with more abundant ingredients. Lithium batteries, for instance, are slowly branching into sodium-based variants, trading high energy density for low cost and security of supply. Cobalt content is being reduced step by step, replaced by nickel or manganese. Transparent conductors that once relied on indium now explore graphene, silver nanowires, or conductive polymers. Each change represents years of microscopic tuning, atoms rearranged to maintain balance between efficiency, stability, and affordability. But few examples capture the ingenuity of substitution better than the saga of magnets. The modern world spins on them, literally. Strong permanent magnets drive motors in everything from laptops to electric cars. The secret lies in the rare earth elements, especially neodymium and dysprosium. These metals, combined with iron and boron, create the most powerful permanent magnets ever engineered. Tiny but mighty, capable of maintaining intense magnetic fields under extreme conditions. Without them, wind turbines would be less efficient and electric motors heavier and slower. However, rare earth is a misleading phrase. These elements aren't especially rare in the Earth's crust, but they're dispersed rather than concentrated, making mining and refining complicated. Environmental concerns, radioactive byproducts, and the dominance of a few producers add layers of risk. As a result, researchers worldwide are searching for alternatives, magnets that perform just as well but rely on more common ingredients. Some look backward in time for inspiration. Ferrets, those familiar black magnets once found on refrigerator doors and speakers, are iron-based and entirely free of rare earths. They're cheap, stable, and non-toxic, but their magnetic strength is modest. Then there's alnico, an alloy of aluminum, nickel, and cobalt. First developed in the 1930s, alnico magnets are strong and can withstand high temperatures, but they can be easily demagnetized, limiting their use in compact high-torque systems. Modern research combines these older materials with advanced microstructural engineering, using nanometer-scale control to enhance their properties. It's a bit like rediscovering an old recipe and seasoning it with quantum precision. Another strategy is to use rare earth elements more efficiently. Engineers design motors and devices that need smaller magnets, or arrange magnetic circuits to achieve the same force with less material. Some even explore magnetic-free designs entirely, like induction systems or mechanical alternatives. Sometimes the smartest magnet, as scientists like to joke, is the one you don't need at all. Behind these efforts is a deeper philosophical shift. For much of industrial history, progress meant using more energy, more metals, more resources. But in the age of critical materials, progress often means using less or using smarter. Every atom becomes valuable, not just for its scarcity but for the ingenuity it inspires. Lightweight magnets and low cobalt batteries aren't simply cost-saving measures, they're expressions of a new kind of responsibility, chemistry guided by foresight. Recycling plays a growing role here too. Magnets from discarded electronics can be dissolved and reconstituted into new alloys, with minimal loss of performance. Battery metals can be recovered through advanced hydrometallurgical and electrochemical methods, sometimes achieving near-total recovery rates. These closed loops transform waste into supply, turning yesterday's devices into tomorrow's resources. When combined with thoughtful substitution and efficient design, they form a quiet blueprint for material resilience. Yet the story of critical materials isn't only about metals or markets, it's also about perspective. Each time science approaches a bottleneck, it discovers not just a workaround, but a lesson in creativity. The concept of criticality teaches humility, that no resource is infinite, no system completely isolated. The smallest mineral grain in a remote desert might connect to the clean energy ambitions of an entire continent. As technology grows more complex, the world's dependency web tightens. The periodic table becomes less a static chart and more a living economy of relationships between abundance and scarcity, innovation and restraint, nature and necessity. We are learning to think of the elements not just as substances, but as participants in an ongoing negotiation between what the Earth provides and what civilization demands. Resilience in that relationship doesn't come from abundance alone, it comes from flexibility, the ability to adapt, to substitute, to recycle, and to imagine new solutions. It's chemistry's version of evolution. Just as life once diversified to survive, our material world is now diversifying to endure. Somewhere in a laboratory, an engineer watches as a newly designed magnet clings tightly to a piece of steel. It's lighter, cheaper, and entirely free of rare earths. It may never make headlines, but in that small moment something shifts. Humanity takes one quiet step toward a future that uses the periodic table not as a list of limits, but as a canvas of possibilities, where every element, critical or not, plays its part with balance and grace. For most of human history, a mine was a hole in the ground. It was a place of dust, noise, and excavation, where people dug into the Earth's crust to pull out the raw materials that built their world. But today, a new kind of mine is emerging, one that doesn't scar landscapes or reach into the depth of the planet. Instead, it exists all around us, in plain sight, built from the bones of modern civilization. It's called urban mining, the practice of recovering valuable materials from the products and structures of our daily lives. Every city is now a kind of geological formation, layered not in sediment and stone, but in steel, glass, copper, and plastic. The buildings, vehicles, and electronics that fill our streets contain vast quantities of refined resources, far more concentrated than the ores that once supplied them. A single ton of discarded smartphones can contain up to 100 times more gold than a ton of natural ore. Old computers and circuit boards hold silver, palladium, and rare earth metals in measurable abundance. Even household wiring, appliances, and fluorescent lamps hold reserves of copper, aluminum, and phosphors, waiting quietly in drawers, garages, and landfills. The idea of mining a city may sound poetic, but it's also practical. Traditional mining consumes enormous amounts of energy and water, while releasing carbon dioxide and chemical waste. By contrast, extracting metals from discarded products can use a fraction of that energy and leave a much smaller environmental footprint. Urban mining isn't about digging deeper, it's about thinking smarter. The process begins with careful recovery. Devices that have reached the end of their lives, phones, laptops, appliances, even cars, are collected and disassembled. In some facilities, human workers gently remove valuable components. In others, robotic systems sort and separate materials with uncanny precision. Screws and clips are prized here. They allow easy disassembly without destroying the parts inside. Glued, welded, or sealed designs, by contrast, make recovery costly and wasteful. It turns out that a good recycling system often begins at the drawing board, not the scrapyard. Designing for repair and reuse means that objects can live longer before they're taken apart, and when they finally are, every piece can find its way into a new form. After disassembly, materials go through a sequence of recovery steps. Metals are often shredded and sorted using magnetic or optical systems. Plastics are classified by type and color. Circuit boards and mixed materials are processed through hydrometallurgy, dissolving metals in controlled chemical baths, or through electro-refining, where electric currents draw pure metal from solution. Each step is a kind of choreography, turning chaos into order, waste into resources. It's tempting to imagine recycling as simple: melt, purify, reuse. But in reality, it's a delicate art. Every material behaves differently when heated or dissolved. Some alloys separate easily, others cling together like stubborn friends. Plastics, too, vary in chemistry, and blending them often produces poor results. That's why the new frontier in recycling focuses as much on design as it does on recovery. When engineers choose materials that can be separated and reused without complex treatment, the entire system becomes more efficient. One of the most promising trends is design for circularity. Instead of treating products as disposable, manufacturers now envision them as temporary configurations of valuable matter. Labels, digital tags, and standardized components make it easier to identify and recover parts later. Some companies use digital passports, small chips or QR codes embedded in devices, to store information about materials and origins. When a product reaches a recycling facility, that information can guide separation and processing automatically. The result is a world where even the smallest object remembers how to be reborn. Several real-world initiatives already show how effective this can be. In Japan, discarded electronics were collected to create the medals for the Tokyo 2020 Olympics, symbolically turning consumer waste into symbols of achievement. In Sweden, large-scale take-back schemes for household appliances ensure that most metals are recovered and reintroduced into production. The European Union's right to repair policies encourage longer product lifespans, while cities like Amsterdam and Singapore are experimenting with urban mines, dedicated facilities designed to harvest and reprocess materials from local waste streams. Circular supply chains are also expanding into industry. Electric vehicle manufacturers now partner with battery recyclers to reclaim lithium, nickel, and cobalt for reuse. Construction firms salvage steel beams, glass panels, and fixtures from old buildings before demolition, drastically cutting raw material demand. Even textiles, once considered low-value waste, are being chemically recycled into new fibers. Slowly, the idea of disposal is losing its finality. Yet urban mining isn't just about economics or engineering, it's about mindset. Humanity once viewed the Earth as an endless supplier. Now we're learning to see it as a finite partner, one whose gifts must be cycled, not consumed. Mining no longer needs to mean destruction. It can mean recovery, restoration, and continuity. The ore veins of the 21st century run not through mountains, but through our own creations. If you look closely, you might see the poetry in it. A phone that once sat forgotten in a drawer becomes part of a wind turbine blade. A worn-out cable finds its copper reborn in an electric bus. Plastic bottles reform into fibers for clothing. It's a kind of modern alchemy, not the mythical transformation of lead into gold, but the very real conversion of waste into worth. The environmental stakes are high. Every ton of recycled aluminum saves roughly 95% of the energy required to produce it from ore. Recycled steel cuts carbon emissions by more than half. Precious metals recovered from electronics prevent the need for new, damaging mines. Urban mining, done thoughtfully, could meet a significant share of future material demand while preserving the natural landscapes that once bore the cost of our progress. Still, it's not a perfect system. Collection remains uneven. Informal recycling in developing regions can expose workers to toxic materials. Ensuring safety and fair labor practices is as important as the chemistry itself. True circularity requires cooperation across design, policy, and public behavior. The willingness to view materials not as single-use, but as chapters in a long, continuous story. That story is slowly taking shape. Where the past century prided speed and novelty, the next may celebrate durability and return. Products will be designed with endings in mind, not as waste, but as beginnings for something else. Cities will evolve from consumers into custodians, turning their own discarded infrastructure into reservoirs of possibility. When future historians look back, they might note that the great minds of the 21st century weren't carved into mountains or deserts, but built into streets, homes, and devices. Humanity learned, finally, that the true wealth of a planet lies not only beneath its crust but within its creativity. Future may not lie under mountains but beneath our fingertips, in the quiet realization that nothing, not even waste, has to be the end of the story. For most of history, mining has been an act of force. The image is familiar: drills, dynamite, and deep pits carved into the Earth's crust, pulling out raw materials with sweat and machinery. It's a process that has built civilizations, but it has also left scars, vast tailings, toxic runoff, and landscapes stripped of their quiet balance. Traditional mining is energy-intensive and chemically harsh, relying on brute strength to separate value from stone. Yet, as technology and environmental awareness evolve, a new philosophy is taking shape, one that sees extraction not as conquest, but as cooperation. Today, scientists are learning to ask a gentler question. What if we could coax metals out of the earth instead of forcing them? What if chemistry could be subtle, efficient, and kind to the environment? This is the heart of a quiet revolution. The rise of bioleaching, brine extraction, green solvents, and selective membranes. Together, these approaches form a movement toward extraction by finesse rather than force. Let's begin with the smallest workers of all, microbes. Hidden in soil, hot springs, and even deep underground mines are bacteria that thrive on minerals. For them, what we call ore is dinner. They oxidize metal sulfides to gain energy, releasing soluble metal ions in the process, effectively digesting rock into recoverable solution. This technique, known as bioleaching, uses natural microbial metabolism instead of smelters or acid baths. Bioleaching isn't new. It's been used commercially for decades to extract copper from low-grade ores that would otherwise be uneconomical, but its potential reaches far beyond copper. Researchers have identified bacteria that can liberate nickel, cobalt, zinc, and even precious metals from waste streams. Some can tolerate extreme acidity, others survive at high temperatures, and a few even thrive on electronic waste, dissolving metals from discarded circuit boards. They are living chemical factories performing complex oxidation-reduction reactions with perfect precision and zero salary requirements. Nature's smallest miners work for free, and they never strike. The advantages are compelling. Bioleaching uses minimal energy, produces less air pollution, and can often take place at ambient temperatures and pressures. It transforms heaps of tailings, those grey mounds of leftover ore, into second chances for resource recovery. It's not fast. Microbial colonies can take weeks or months to process material that smelting could handle in hours. But the trade-off is gentleness, a process that works with nature's rhythms instead of against them. Beyond microbes, the next frontier lies in fluids, specifically in the overlooked reservoirs of the sea and the Earth's crust. Oceans contain almost every element in the periodic table, though most are heavily diluted. Extracting them is like trying to catch whispers in a storm, but new technologies are making it more plausible. Seawater holds immense quantities of lithium, magnesium, and uranium in trace concentrations. Each litre contains only a few milligrams, but multiply that by the volume of the oceans, and the potential becomes staggering. The key is selectivity, finding ways to capture specific ions without harvesting unwanted ones. Scientists are developing membranes and sorbent materials that act like sieves for atoms. Some are coated with organic molecules that latch onto lithium while ignoring sodium, which is chemically similar but far more abundant. Others use electricity to drive selective migration through membranes, pulling valuable ions from geothermal brines or desalination wastewater. These sources, once considered useless or problematic, could become quiet supply lines for essential materials. Geothermal brines, in particular, are promising. The hot, mineral-rich fluids pumped from Earth's depths for geothermal energy are naturally laden with lithium, zinc, and rare metals. Rather than discarding them after power generation, new systems capture their dissolved wealth. It's a beautiful synergy, using one form of renewable energy to gently harvest another kind of resource. Still, there's another transformation underway. Not in the source of metals, but in the chemistry of extraction itself. Traditional hydrometallurgy, which relies on strong acids and bases to dissolve minerals, often creates toxic byproducts. Modern chemists are reimagining these reactions through solvometallurgy, the use of green solvents, ionic liquids, and deep eutectic mixtures to replace aggressive reagents. These tailored fluids dissolve and separate metals with remarkable efficiency, yet can be recycled with minimal waste. Imagine replacing the sharp scent of sulfuric acid with a mild, biodegradable solvent that can be reused dozens of times. Ionic liquids, for example, are composed entirely of ions, but they're stable, non-volatile, and tunable. You can adjust their properties by altering their chemical recipe. They can selectively extract specific metals, such as cobalt from lithium-ion batteries, leaving the rest untouched. The result is chemistry that feels almost surgical, clean, precise, and calm. Membrane technology complements this approach perfectly. Instead of relying on bulk chemistry to do the heavy lifting, membranes achieve separation through structure. Think of them as sieves at the molecular scale, with pores so fine they can discriminate between ions based on size, charge, or hydration shell. In electrochemical setups, these membranes can guide certain metals to specific electrodes, concentrating them without excess heat or chemicals. One striking example is electrodialysis, a process that uses alternating membranes to move ions in an electric field. It's being explored for lithium extraction from brines, where it can replace evaporation ponds that take years and consume vast land areas. Another is selective polymer membranes used for recovering rare earth elements from industrial waste. These methods reduce environmental disturbance, shorten processing times, and conserve water. The quiet virtues of modern metallurgy. The biggest challenge, of course, is scale. Microbes and membranes may sound miraculous, but turning laboratory success into global supply chains is no small task. Bioleaching requires controlled conditions, consistent microbial health, and careful waste management. Brine and seawater extraction face economic hurdles due to low concentrations. Green solvents, though effective, can be expensive to produce in bulk. The path ahead will involve refining these technologies until they match the throughput of conventional mining without inheriting its drawbacks. But the promise is too compelling to ignore. The old paradigm of extraction, dig, crush, burn, separate, is giving way to one defined by patience and precision. A future mine might look less like a canyon and more like a greenhouse or a lab. Quiet, clean, and humming softly with the sound of flowing fluids and microbial life. Instead of smoke and dust, there will be circuits and cultures, filters and feedback loops. The tools of mining will become instruments of stewardship rather than disruption. It's an inversion of philosophy as much as of process. Humanity's relationship with the earth is shifting from command to conversation. Where once we took by force, we now ask politely, and often get a better answer. The minerals that shape the industrial world can still sustain the future, but only if we learn to extract them with respect, not recklessness. So the story of mining is slowly being rewritten. The deep rumble of machinery is joined by the quiet work of microbes, the delicate filtration of membranes, and the silent shimmer of green chemistry. Together, they signal a turning point, one where extraction evolves from an act of domination into an act of design. The future of mining may not roar, it may simply hum. Nature, after all, has been refining this art for billions of years. Rivers dissolve minerals gently, microbes process metal ions without waste, and geothermal vents recycle elements through endless cycles of heat and flow. We are finally catching up to that wisdom. Extraction, it turns out, was never meant to be violent. It was meant to be clever. And as the world transitions towards sustainability, perhaps the greatest achievement won't be how much we can take from the planet, but how gently we can do it. Mining, once defined by force, is learning the elegance of restraint, proof that even in industry, patience can be revolutionary. The future of extraction belongs not to the strongest, but to the most refined. It is a world where chemistry becomes choreography, where precision replaces pressure, and where every drop, every microbe, and every atom has its role in the quiet symphony of renewal. Hydrogen is the universe's favourite element. It makes up roughly 3/4 of all normal matter, fills stars with light, and was the first atom to ever exist. It's also surprisingly shy, always clinging to other atoms, never content to stay alone. On Earth, it hides in water and organic molecules, waiting to be coaxed free. And when it is, hydrogen becomes something extraordinary, a clean carrier of energy that could help the world drift away from fossil fuels. At first glance, hydrogen seems almost too good to be true. When burned or combined with oxygen in a fuel cell, it produces only water as a byproduct. No carbon dioxide, no soot, no lingering pollution, just a puff of vapor that vanishes harmlessly into the air. The energy density by weight is remarkable. A single kilogram of hydrogen contains more energy than 2 kilograms of gasoline. The problem, as with so many clever ideas, lies in the details. The smallest element has some big logistical issues. Producing hydrogen can be done in several ways, each with its own trade-offs. The simplest is steam methane reforming, where natural gas is reacted with high-temperature steam to produce hydrogen and carbon dioxide. It's efficient, established, and, unfortunately, carbon-intensive. To make hydrogen truly clean, we need methods that skip the fossil step altogether. One of the most promising alternatives is electrolysis. In this process, electricity splits water into hydrogen and oxygen, a reaction as elegant as it is ancient. If the electricity comes from renewable sources, wind, solar, hydro, the result is green hydrogen. Every bubble of gas becomes stored sunlight, a portable form of clean energy. The challenge is scale and cost. Electrolyzers require expensive materials, and electricity itself still carries a price. Yet progress is steady, and costs are falling year by year as new catalysts and membranes make the process more efficient. There are also thermochemical routes that use heat from concentrated solar energy or nuclear reactors to drive chemical cycles that split water. Some designs pair metal oxides that absorb and release oxygen in alternating steps, turning sunlight directly into hydrogen with almost no electricity at all. It's a quiet reminder that energy can be transformed in more ways than we often imagine, through heat, light, and chemistry working in tandem. Once hydrogen is produced, the next challenge begins: storing it. Hydrogen gas is exceptionally light, so light that it slips through materials that seem solid and leaks away with the determination of a magician's escape act. To store it compactly, engineers use one of 3 main strategies: compression, liquefaction, or absorption in materials. Compressed hydrogen is squeezed into high-pressure tanks, sometimes at over 700 times atmospheric pressure. It works, but it's energy-intensive and requires thick, reinforced vessels. Liquefying hydrogen involves cooling it to just 20 degrees above absolute zero, colder than the surface of Pluto, to condense it into a dense cryogenic liquid. The result is efficient for transport but demands constant insulation to prevent boil-off. A more elegant option involves metal hydrides, materials that can absorb hydrogen into their atomic structure like a sponge soaking up water. When heated, they release it again, providing a safe and stable storage cycle. Some hydrides, such as magnesium-based compounds, can hold several % of their weight in hydrogen. The search continues for the perfect balance between weight, temperature, and release speed, but the idea remains alluring: storing hydrogen not in a tank but inside a material itself. Even if storage is solved, hydrogen has another quirk: it can make metals brittle. Pipelines designed for natural gas can weaken when exposed to hydrogen atoms that diffuse into their structure, creating microscopic cracks. This phenomenon, called hydrogen embrittlement, sounds dramatic but is simply the result of atoms slipping into places they don't belong. Engineers are now developing new alloys, coatings, and polymers to safely contain hydrogen across long distances. It's a reminder that sometimes progress depends not just on what we invent, but on how well our inventions get along with physics. One way around these challenges is to carry hydrogen in disguise. Enter ammonia, a molecule made of nitrogen and hydrogen. For over a century it has been produced at industrial scale to make fertilizers through the Haber-Bosch process, which itself consumes large amounts of hydrogen. Now scientists are looking to reverse the relationship. Use ammonia as a carrier for hydrogen instead. Nitrogen binds hydrogen atoms tightly, allowing the gas to be stored and transported as a liquid under relatively mild conditions. When needed, ammonia can be cracked back into hydrogen and nitrogen using catalysts. Ammonia offers several advantages. It's easier to store than pure hydrogen, has an existing global infrastructure, and can even be used directly as a fuel in specialized engines or fuel cells. However, it's not without complications. Ammonia is toxic and pungent, and the cracking process requires energy and careful control. Still, its potential as a large-scale hydrogen carrier is being tested in pilot projects around the world, from shipping ports to power stations. Another emerging solution involves liquid organic hydrogen carriers, or LOHCs. These are special organic liquids, often similar to common industrial solvents, that can chemically absorb hydrogen when exposed to it under pressure. Later, when heated with a catalyst, they release the hydrogen again, returning to their original form. Think of them as reusable chemical bottles for hydrogen, stable and easy to handle. They can be transported through normal fuel infrastructure and stored at room temperature without risk of embrittlement or evaporation. It's not yet the simplest option, but it may prove ideal for balancing storage and transport in a global hydrogen economy. Infrastructure remains the invisible backbone of this entire endeavor. Hydrogen pipelines, fueling stations, and storage depots all require new materials and safety standards. Unlike oil or gas, hydrogen flames are nearly invisible and spread rapidly, demanding careful detection systems. Fortunately, these challenges are well understood, and early projects have shown that with proper design, hydrogen can be handled as safely as any conventional fuel. Globally, hydrogen's identity is shifting. Once it was mainly an industrial feedstock, used to refine oil, produce ammonia, and make methanol. Now it's being reimagined as an energy vector, a medium for carrying renewable energy where it's needed. Excess wind or solar power can create hydrogen through electrolysis, storing energy that would otherwise be wasted. Later, that hydrogen can be converted back to electricity in fuel cells, used for heating or combined into synthetic fuels for ships and aircraft. Japan, South Korea, and parts of Europe are already investing heavily in hydrogen infrastructure, while research continues into making it cleaner and cheaper to produce. The dream is of a circular energy system, one that quietly moves electrons in chemical form, gathering energy when it's abundant, releasing it when it's needed. Hydrogen sits at the center of that dream, not as a silver bullet, but as a graceful intermediary, connecting the rhythms of nature with the needs of technology. There's something almost poetic about it. The universe's simplest atom, forged in the first moments after the Big Bang, may yet play a starring role in humanity's sustainable future. It is as if the cosmos left behind a clue, a tiny, elusive element capable of storing sunlight, wind, and heat in one invisible breath. Hydrogen reminds us that motion itself can be an act of elegance. Whether bound in ammonia, absorbed in metal, or flowing through a membrane, it carries energy silently, without smoke or flame. And as the world slowly learns to use it wisely, we might discover that the future of energy isn't noisy or polluting at all. It's quiet, colourless, and beautifully simple. The chemistry of motion, written by the smallest of all elements. For all our efforts to harness the power of the Earth, humanity's most concentrated source of energy still comes from imitating the stars, or at least their smaller cousins. At its heart, nuclear energy is the art of persuading the atom itself to share its hidden fire. Two main paths exist for doing this: fission and fusion. One works by splitting atoms apart, the other by forcing them together. Both draw from the same well of physics, the deep balance between matter and energy that Einstein so elegantly described over a century ago. Fission, the older and more familiar of the two, is the controlled splitting of heavy atomic nuclei. When uranium-235 absorbs a stray neutron, it becomes unstable and divides into smaller nuclei, releasing energy and more neutrons. Those new neutrons strike other uranium atoms, continuing the process in a self-sustaining chain reaction. Each event liberates a tiny burst of energy, but multiply that by countless trillions of atoms, and the result is staggering. A single kilogram of uranium can release as much energy as several million kilograms of coal. That astonishing energy density is why nuclear fuel can power entire cities from fuel rods small enough to fit in a backpack. Thorium, another potential fuel, follows a different but equally elegant path. It's fertile rather than directly fissile, meaning it can't sustain a chain reaction on its own, but can be converted into uranium-233 when it absorbs a neutron. This thorium cycle produces less long-lived waste and carries lower risks of weaponization, making it attractive for future reactor designs. For decades, it's been the quiet understudy of nuclear energy, safe, abundant, and waiting patiently in the wings. The key to nuclear power lies not only in splitting atoms, but in managing what happens afterward, the fuel cycle. The simplest approach, called the once-through cycle, uses uranium fuel until it's no longer efficient, then stores the spent fuel as waste. It's straightforward, but it leaves much of the potential energy untapped. Only a small fraction of the uranium's energy content is used before disposal. A more sophisticated option is the closed fuel cycle. In this model, spent fuel is chemically reprocessed to extract usable isotopes like plutonium and uranium, which can be recycled into new fuel. What remains, mainly fission products and minor actinides, can then be vitrified or locked into glass for long-term storage. Vitrification is chemistry's answer to immortality. The waste is encased in durable, non-reactive glass logs that can safely sit for millennia without leaching. Some countries, notably France and Japan, already use partial reprocessing to stretch their uranium supplies, while others focus on developing fast reactors that can burn these recovered materials more efficiently. This looped approach mirrors the broader theme of modern energy, closing circles rather than drawing lines. Instead of taking and discarding, reprocessing allows the same atoms to be used again and again. Even within the intense world of nuclear physics, recycling is making a quiet comeback. But for all the progress fission offers, its sibling, fusion, remains the dream that refuses to fade. Where fission splits heavy nuclei, fusion merges light ones. It's the process that powers the stars, the same reaction that turns hydrogen into helium in the sun's core. When two isotopes of hydrogen, deuterium and tritium, collide under immense pressure and temperature, they fuse into helium and release enormous amounts of energy. The catch is that replicating this process on Earth requires conditions rivaling the interior of the Sun, temperatures above 100 million degrees Celsius, and confinement strong enough to keep the plasma, that superheated soup of charged particles, from touching any solid surface. Contain a miniature sun, people say. What could possibly go wrong? The answer, so far, has been mostly technical difficulties. Fusion is famously difficult to sustain. The plasma writhes like a living creature, trying to escape any magnetic cage built to hold it. Scientists have spent decades taming these instabilities using tokamaks and stellarators, donut-shaped chambers lined with magnets that swirl the plasma in controlled loops. Projects like ITER in France, and newer compact reactors in the United States, Japan and the United Kingdom represent the world's most ambitious attempts to make fusion a practical reality. Each one is a monument to patience. Machines built to test the limits of physics and persistence alike. Despite the challenges, progress is genuine. Experiments have achieved record levels of confinement, approaching the point of net energy gain, where the fusion reaction produces more energy than is required to sustain it. Laser-driven fusion, such as that pursued at the National Ignition Facility in California, has even achieved ignition, the moment when the reaction becomes self-sustaining for an instant. While it's not yet ready for power plants, the underlying science has crossed important thresholds. What was once a distant hope is slowly becoming a tangible technology. Fusion's fuel supply also holds a poetic simplicity. Deuterium, one of its key ingredients, is abundant in seawater. Every litre of ocean holds enough to release massive energy if harnessed efficiently. Tritium, the rarer isotope, can be bred from lithium using neutron reactions inside the reactor itself. This means that future fusion plants could, in principle, generate their own fuel using Earth's most common resources. And beyond deuterium and tritium lies another possibility: helium-3, a light isotope found in trace amounts on Earth, but more abundant in lunar soil and the outer planets. It could provide a cleaner fusion reaction, with minimal radioactive byproducts, though collecting it would require a cosmic-scale mining effort. For now, helium-3 remains more the language of science fiction than of engineering, but it keeps the imagination bright. Both fission and fusion share a central challenge beyond their reactions: materials. The very neutrons that carry their power also wear down the structures that hold them. Inside reactors, metals and ceramics endure relentless bombardment that can displace atoms, alter their crystal structures, and cause brittleness over time. Developing materials that can survive years in this hostile environment is an entire branch of modern science. Self-healing ceramics, radiation-tolerant steels, and smart coatings that absorb or deflect damage are all part of the quiet arms race between durability and decay. These materials will also shape how future reactors look. Some designs aim for modularity, small sealed reactors that can be built in factories and delivered ready to operate. Others envision molten salt or liquid metal cooling systems that allow for higher efficiency and inherent safety. In all cases, the goal is to transform nuclear energy from something monumental into something graceful, reliable, and quietly powerful. Despite the promise, nuclear energy has always carried social and political complexity. Safety, waste, and proliferation remain genuine concerns, demanding transparency and trust. The balance between innovation and caution must be maintained with care, not through fear, but through patience. In physics, as in policy, rushing rarely leads to good reactions. Yet when viewed through a wider lens, both fission and fusion embody a kind of cosmic symmetry. One releases the energy locked in heavy atoms, The other recreates the process that forged those atoms in the first place. Between them lies the full cycle of matter itself, from the collapsing heart of a star to the engineered heart of a reactor. Both are reminders that the forces shaping the universe are the same ones humming quietly on Earth, waiting for us to understand them fully. If humanity succeeds, the result will not be a blinding leap forward, but a steady glow, power drawn from the same rules that guide the cosmos. And perhaps that's fitting. True progress often arrives not with explosions, but with balance. The most elemental power is patience, in atoms, in stars, and in us. Every spark that powers modern life begins in a surprisingly simple box. A battery is, at its heart, a container for chemistry in motion, a quiet mediator between potential and flow. Inside, it holds four main parts: an anode, a cathode, an electrolyte, and a separator. The anode releases electrons, the cathode receives them, and the electrolyte allows ions, the charged particles, to drift between the two. The separator keeps everything from shorting out, while still letting ions move freely. It's a simple dance, electrons gliding through wires, while ions waltz through liquid or solid pathways, all perfectly balanced. The beauty of the battery lies in its reversibility. When you use it, chemical reactions drive electrons outward to power your phone, car, or laptop. When you recharge it, that same flow reverses, restoring the original arrangement of atoms inside. A battery is like a heartbeat of chemistry: contraction, release, contraction again. Each pulse pushes the modern world a little further. At the center of that heartbeat is lithium. Light, reactive, and energetic. Lithium is the reigning champion of portable power. Lithium-ion batteries dominate everything from smartphones to electric vehicles, largely because of their remarkable energy density. They store more energy per kilogram than nearly any other rechargeable chemistry. Inside them, lithium ions shuttle back and forth between a carbon-based anode, often graphite, and a metal oxide cathode containing elements like cobalt, nickel, or manganese. Each trip of the ions corresponds to the flow of electrons outside, powering your favorite gadget or carrying your car quietly down the road. But the success of lithium-ion technology comes with a cost, both literal and environmental. Lithium itself is not especially rare, but its extraction from salt flats and hard rock mines consumes vast quantities of water and energy. Cobalt, another key ingredient, is often sourced from regions where mining conditions raise ethical and ecological concerns. Nickel and manganese too carry their own environmental footprints, and so the global race to electrify transportation has revealed a paradox. In solving one problem, carbon emissions, we risk creating others if we are not careful with materials. This realization has sparked a wave of innovation aimed at broadening the palette. Scientists are exploring ways to reduce or even eliminate cobalt from cathodes, replacing it with more abundant metals like iron or aluminum. Others are venturing beyond lithium altogether, reviving an old contender, sodium. Sodium-ion batteries operate on the same principle as their lithium cousins, but with one key difference. Sodium atoms are larger and heavier. They carry less energy per kilogram, but they're vastly more available. Sodium, after all, is the same element that flavors the sea and seasons your dinner. It can be sourced almost anywhere, cheaply and safely. This makes sodium-ion batteries particularly appealing for stationary applications, such as storing solar or wind energy on the grid, where size and weight matter less than cost and sustainability. Recent breakthroughs have narrowed the performance gap between sodium and lithium cells. New electrode materials can handle sodium's bulk without cracking, and clever electrolytes improve efficiency and lifespan. Some early models are already entering the market, promising to deliver large-scale energy storage without relying on scarce or expensive metals. It's a quiet revolution, not about speed or glamour, but about balance and availability. Yet even sodium may not be the final word. Beyond the familiar alkali metals lie a host of alternative chemistries waiting in laboratories. Magnesium and calcium, for example, can carry 2 charges per ion instead of 1, theoretically doubling energy density. Zinc-based systems offer exceptional safety and simplicity, operating in water-based electrolytes that cannot catch fire. Aluminum-ion designs are being tested for ultra-fast charging. Each approach brings its own quirks. Some struggle with sluggish ion movement, others with unstable interfaces. But together they show that the world's energy future will not hinge on a single element. It will be a blend, a palette of chemistries tuned to each purpose. Perhaps the most eagerly watched development, however, is solid-state technology. In a traditional lithium-ion cell, the electrolyte is a liquid or gel, often flammable and sensitive to heat. A solid-state battery replaces it with a solid ceramic or polymer that conducts ions without risk of leakage or combustion. These solid electrolytes could eliminate one of the main safety concerns of modern batteries, while enabling denser, longer-lasting designs. But as always, nature resists perfection. Lithium, ever the wanderer, tends to form thin metallic filaments known as dendrites during charging. These needle-like structures can grow through the separator and short-circuit the battery, a microscopic lightning strike waiting to happen. Solid-state materials, though stronger, aren't immune. Researchers are experimenting with flexible ceramics, layered composites, and self-healing interfaces to stop dendrites in their tracks. Each improvement brings the dream of safer, faster charging batteries a little closer. Even as new chemistries bloom, one challenge lingers across them all: recycling. The world produces hundreds of thousands of tons of spent batteries each year, containing valuable metals that too often end up as waste. Extracting these materials is tricky. Batteries are complex mosaics of chemicals and casings. Separating them safely requires advanced techniques. Hydrometallurgy, dissolving metals in controlled solutions, is gaining ground, as are direct recycling methods that recover entire electrode materials intact. These innovations aim to keep lithium, cobalt, nickel, and other precious elements cycling through the economy rather than leaking back into the ground. The need for recycling grows as batteries spread into every corner of life. Electric cars demand power packs that last for decades, then find second lives as home storage units before being fully recycled. Grid batteries must handle daily charge-discharge cycles for years, while wearables and medical devices require tiny, flexible cells that can bend and twist without losing performance. Each application favors a different chemistry, some emphasizing energy density, others safety, cost, or durability. The battery industry, once narrow in focus, has become a vast landscape of specialization. If the 20th century was defined by oil and combustion, the 21st may well be shaped by ions and flow. Energy no longer roars and burns, it glides silently through cables, stored in lattices of carbon, silicon and metal oxides. The shift is more than technological, it's philosophical. We are learning to treat energy as something to be managed gently, not consumed violently. And in that quiet transformation, batteries become more than devices. They're metaphors for balance, storing energy when it's plentiful, releasing it when it's needed, always returning to equilibrium. They teach us that progress can be cyclical, not linear, and that even power can rest between pulses. From lithium's light touch to sodium's abundance, from solid-state dreams to humble recyclers, the world's battery palette continues to expand. Each chemistry adds a new color to the future's canvas, painting a picture of resilience, diversity, and calm innovation. Energy, like sleep, needs something steady to hold it, and the battery, with its patient rhythm of charge and release, may be the gentlest heartbeat of all. Every chemical reaction is a little bit like a conversation. Some atoms meet and instantly connect, while others need a patient friend to introduce them and smooth out the awkward silences. In chemistry, that friend is called a catalyst, a substance that makes reactions happen faster or under gentler conditions without being consumed in the process. It's the quiet negotiator of the molecular world, speeding up transformations that might otherwise take centuries or never happen at all. Catalysts are everywhere, quietly shaping modern life. The fertilizer that feeds much of the world's agriculture comes from ammonia, produced through the Haber-Bosch process, a reaction that relies on iron-based catalysts to help nitrogen and hydrogen combine under heat and pressure. The gasoline or diesel that once powered vehicles was refined through catalysts that cracked long hydrocarbon chains into usable fuels. Even the air we breathe indoors is often cleaned by catalytic converters that break down pollutants into harmless gases. Without catalysts, civilization would run sluggishly. Food production would falter, fuel would waste, and nearly every branch of industry would slow to a crawl. Yet despite their importance, designing catalysts has always been an intricate form of trial and error. Chemists might test hundreds of metal combinations or surface structures to find one that performs just right. Each change in composition or shape can alter how reactants stick, move, and transform on the surface. It's an enormous puzzle with billions of possible arrangements, too complex to explore by hand. For decades, researchers relied on intuition, experience, and a bit of luck. But now, a new approach is rewriting that tradition. It's called inverse design, and it flips the process upside down. Instead of starting with materials and seeing what they do, scientists begin with the goal, the desired reaction, and work backward to determine the perfect catalyst for it. Using quantum mechanical models and computational chemistry, they can predict how different surfaces will interact with molecules. Artificial intelligence then scans millions or even billions of possibilities in silico before anyone lifts a beaker. It's chemistry's version of matchmaking, bringing molecules together smoothly. The computer plays Cupid, searching the vast landscape of potential catalysts to find the one that can coax two reactants into partnership. The result isn't random discovery, it's targeted innovation. This shift has transformed how new catalysts are found. In the past, developing one might take years of painstaking synthesis and testing. Now, machine learning algorithms can evaluate candidates in days, ranking them by predicted performance, stability, and cost. The laboratory becomes a confirmation step rather than a fishing expedition. Some researchers describe it as moving from Edison's workshop to nature's blueprint. Less tinkering, more reasoning. One example comes from efforts to reduce carbon dioxide, that stubborn greenhouse gas, into useful products. Traditional catalysts like copper can convert carbon dioxide into fuels or alcohols, but with mixed efficiency. By using inverse design and artificial intelligence, chemists have identified specific atomic arrangements, particular ratios of copper and other metals, that favour the formation of valuable compounds like ethanol or ethylene while minimising waste. These insights have produced catalysts that are both faster and cleaner, turning a waste gas into a feedstock for sustainable chemistry. The same approach is accelerating research in ammonia synthesis, hydrogen production, and fuel cell design. For instance, platinum has long been the gold standard for catalytic performance, especially in fuel cells, but it's expensive and rare. Machine learning has revealed alternative alloys, blends of nickel, cobalt, or molybdenum, that approach or even surpass platinum's efficiency at a fraction of the cost. Such discoveries illustrate how data-driven design can free chemistry from the limits of intuition alone. At the frontier of this field are single-atom catalysts, systems where individual metal atoms are anchored to a support surface, each one acting as its own reaction site. Because every atom participates directly, there's no wasted material, and performance can be tuned with atomic precision. Imagine a city where every worker contributes at full capacity. No slack, no redundancy, only perfect coordination. Single-atom catalysts achieve that level of efficiency, squeezing maximum output from minimal input. Another promising class involves high-entropy alloys. These are metallic mixtures containing 5 or more elements blended in nearly equal proportions. At first glance, that might sound like chaos, but the disorder itself creates unique stability and resilience. The varied atomic sizes and bonding preferences produce surfaces with countless microenvironments, each offering slightly different catalytic properties. The result is a material that can adapt dynamically to complex reactions, remaining active where simpler alloys would fail. It's like giving a catalyst multiple personalities. One of them is almost always suited to the job. Nature, of course, has been doing this kind of design for billions of years. Enzymes, biological catalysts, perform chemistry so elegantly that even the most advanced synthetic systems look clumsy by comparison. Enzymes can assemble molecules atom by atom, at room temperature, in water, and with zero waste. They are models of efficiency and selectivity, evolved through eons of trial and refinement. Today, scientists are learning from these natural templates, creating enzyme-inspired catalysts that combine biological principles with inorganic durability. By mimicking enzyme pockets or flexible active sites, chemists can bring a touch of life's precision to industrial processes. Some of the most exciting research now blends these worlds. Artificial intelligence doesn't just identify catalysts, it learns from them, recognizing hidden patterns that even experienced scientists might miss. Algorithms trained on vast databases of reaction outcomes can propose entirely new families of materials, ones that don't yet exist in nature or on the periodic table. This feedback loop between experiment and computation forms a virtuous cycle. Each discovery teaches the model, and each model accelerates the next discovery. The pace is breathtaking, but it also invites a new kind of humility. As design becomes automated, chemists shift from experimenters to curators, guiding machines toward meaningful questions. The goal isn't to replace creativity, but to amplify it. After all, a computer can search parameter space, but only a human can decide what's worth finding. The implications of efficient catalysis extend far beyond laboratories. Better catalysts mean cleaner energy, less waste, and smaller environmental footprints. They can unlock carbon-neutral fuels, biodegradable plastics, and sustainable fertilizers that feed billions without draining the planet's resources. Even small improvements can ripple globally. A catalyst that saves 1% of energy in ammonia production could reduce carbon emissions by millions of tons each year. And yet, the beauty of this science lies in its subtlety. Catalysts don't shout or explode. They don't take center stage in products or technologies. They work quietly, invisibly, and tirelessly, turning potential into progress. In a way, they mirror the best aspects of the natural world: efficient, patient, and understated. So when chemists joke that catalysts are chemistry's version of matchmaking, they're not entirely wrong. These substances create harmony where there was once resistance, arranging molecular unions that would otherwise never occur. They embody a kind of wisdom, the understanding that progress doesn't always come from more energy, but from better timing. The future of catalysis is one of quiet efficiency. Reactions will grow cleaner, materials will last longer, and the line between natural and artificial design will blur into seamless cooperation. Somewhere in the gentle hum of a reactor or the flicker of a computer model, new catalysts are already taking shape, tiny intermediaries that turn possibility into reality, atom by atom, without ever demanding credit for the transformation. If you could hold the heart of modern civilization in your hand, it would probably look unremarkable, a thin grey wafer no larger than a coin. And yet within that wafer lies one of humanity's most astonishing achievements: the control of electrons with almost perfect precision. This is silicon's domain, the quiet foundation of the digital age. From smartphones to satellites, every calculation, click, and conversation begins as a tiny current moving through silicon's ordered lattice. It's humbling to think that all of it begins with sand. Silicon makes up over a quarter of the Earth's crust, most of it locked inside ordinary quartz. Refine that quartz, purify it to extraordinary levels, and you have the raw material for microchips. Silicon's magic lies in its position on the periodic table, a semiconductor balanced between conductor and insulator. Add a trace of impurities, called dopants, and its behavior shifts dramatically. A little phosphorus gives it extra electrons, a little boron leaves it hungry for them. Arrange these doped regions carefully, and you can create pathways where electrons flow only when asked. That's the transistor, a switch so small and reliable that billions can fit on a single chip. Since the first integrated circuits in the 1950s, this combination of simplicity and control has fueled an unbroken technological acceleration. Silicon earned its crown by being predictable, strong, stable, and easy to work with. Over the decades, engineers learned to etch impossibly fine circuits onto its surface using light and chemistry, shrinking features from millimeters to nanometers. The phrase Moore's Law, the observation that the number of transistors on a chip doubles roughly every 2 years, became a prophecy of progress. But silicon, as miraculous as it is, has limits. As components shrink to atomic scales, heat buildup and quantum interference threaten to blur the distinction between on and off. The next generation of computing materials must handle higher voltages, faster speeds, and more extreme environments without breaking a sweat. Enter the wide bandgap semiconductors, gallium nitride and silicon carbide. These materials can tolerate higher electric fields and operate at greater temperatures than silicon ever could. Gallium nitride in particular is transforming power electronics, the circuits that convert and regulate electricity. It allows smaller, faster and more efficient chargers and inverters, which is why a modern phone charger can be no larger than a matchbox yet deliver incredible power. Silicon carbide, on the other hand, thrives in harsh conditions. It's used in electric vehicles and renewable energy systems where heat and stress would destroy ordinary chips. These semiconductors don't replace silicon everywhere, but they extend its reach, letting electrons flow freely in places once considered impossible. Beyond these rugged materials lies an entirely new frontier: quantum materials. Here, electrons are no longer treated as simple particles but as waves, capable of interference, entanglement, and collective behavior. Superconductors are the most famous example. When cooled to near absolute zero, they lose all electrical resistance, letting current flow forever without loss. This phenomenon, discovered by accident in 1911, has become the cornerstone of quantum computing, where superconducting circuits can act as qubits, the quantum equivalent of bits, capable of being both 0 and 1 at the same time. Other quantum materials are even stranger. Topological insulators, for instance, conduct electricity only along their edges while remaining insulating inside. Their electrons behave as if they have no mass, racing around the surface in perfectly ordered loops. These materials could lead to ultra-stable quantum computers immune to many forms of interference, devices that store and manipulate information using the geometry of their own wave functions. Then there are defect centers in diamond, where a single atom of nitrogen or silicon sits inside the carbon lattice, displacing one of the host atoms. These tiny imperfections can trap an electron in a stable quantum state that can be read and controlled with lasers. It's as if the flaw itself becomes a feature, a quantum memory housed inside one of the hardest substances on Earth. Not all new computing materials are exotic or frozen near absolute zero. Some are as thin as a single atom. Graphene, a sheet of carbon atoms arranged in a honeycomb pattern, was isolated for the first time in 2004 using nothing more advanced than adhesive tape and persistence. Despite its humble debut, it turned out to be extraordinary. Stronger than steel, more conductive than copper, and flexible enough to fold. Graphene opened the door to a new family of two-dimensional materials, where electrons move freely in flat planes. Molybdenum disulfide, or MoS2, is one such material. Unlike graphene, it has a natural band gap, which means it can act as a transistor, switching currents on and off. Transparent, flexible, and lightweight, these materials promise a future of bendable displays, wearable sensors, and even transparent solar cells. They combine the elegance of chemistry with the creativity of design, building devices not just in 3 dimensions but in 1 or 2, with precision measured in angstroms. In this new world, imperfections are not merely tolerated, they are engineered. Defects in a crystal lattice can localize electrons, create color centers, or change how light interacts with matter. In quantum devices, these imperfections become deliberate, traps that hold information, sites that anchor photons, or scattering points that tune conductivity. A perfect crystal might be beautiful, but it's often the controlled flaws that make it useful. After all, a diamond owes its sparkle to impurities. Manufacturing at such precision, however, is a monumental challenge. The thinner the material, the more demanding its purity becomes. A single contaminant atom in a billion can alter performance. The clean rooms where chips are born are among the purest environments on Earth, with air filtered 1,000 times more thoroughly than in a hospital. Workers wear full-body suits not to protect themselves, but to protect the materials from them. A single speck of dust could ruin a device worth millions. In this context, it's easy to appreciate the humor. Sometimes a chip's biggest breakthrough is just fewer impurities. Scaling these technologies from laboratory wonders to industrial workhorses requires patience. Quantum computers, for all their promise, still depend on complex cryogenic systems. Two-dimensional materials are fragile, prone to contamination and wrinkles. Even gallium nitride and silicon carbide need specialized fabrication equipment and careful quality control. Progress comes not in leaps but in layers, one atomically thin improvement at a time, and yet the direction is unmistakable. Computing is becoming less about brute force and more about elegance, finding materials that handle electrons with minimal waste, minimal heat, and maximal precision. Each new discovery refines the choreography of charge, turning chaotic motion into organized logic. It's remarkable to consider that every byte of information, every digital heartbeat of modern society, rests on the alignment of atoms. Beneath the flashing screens and cloud servers lies an astonishing simplicity. Electrons following the quiet orders written into crystal lattices. Whether those lattices belong to silicon, gallium nitride, or a sheet of graphene floating in the lab, they all serve the same purpose: to keep the dance of information in perfect time. In the end, computing isn't powered by noise or speed alone. It's powered by structure, by the calm geometry of matter arranged just so. Every device, from the most powerful supercomputer to the smallest smartwatch, owes its life to the disciplined order of well-behaved elements. And in that harmony of electrons and lattices, the modern world finds its rhythm, silent, precise, and endlessly unfolding. Carbon may be the most familiar element of all, a quiet constant in everything from pencils to diamonds, from the food we eat to the air we exhale. Yet its true genius lies in its versatility. A single element, just 6 protons strong, can wear an astonishing number of masks. Under one set of conditions it becomes graphite, soft enough to smear across paper. Under another it transforms into diamond, hard enough to cut steel. The same carbon atoms that form fragile soot can also weave into graphene, a 1-atom thick sheet stronger than anything we can make in bulk. Few elements play such a range of roles with such elegance. That versatility comes from carbon's willingness to bond, to reach out and connect with almost anything, including itself. Each atom can make 4 bonds, creating chains, rings, and lattices in near infinite combinations. From this simple rule arises the entire chemistry of life, the structures of organic molecules, and the materials that underpin modern technology. Carbon is both the poet and the engineer of the periodic table. In diamond, its atoms lock tightly together in a 3-dimensional network. Every bond is identical, every angle perfectly symmetrical, and the result is rigidity, light trapped in solid form. In graphite, by contrast, the bonds form flat sheets of hexagons that slide easily past each other, making it soft and conductive. Peel those sheets down to a single layer, and you have graphene, a marvel of modern materials science. Graphene conducts electricity faster than copper, flexes without breaking, and is nearly transparent. It has inspired dreams of foldable electronics, ultra-efficient batteries, and even space elevators, though the latter may have to wait for the laws of material science to catch up with the imagination. Then there are carbon nanotubes, cylinders of graphene rolled so precisely that they behave like molecular wires. Their strength-to-weight ratio is astonishing, and their ability to conduct both heat and electricity makes them candidates for next-generation electronics and composite materials. Carbon also forms fullerenes, hollow spheres shaped like soccer balls, made entirely of interconnected hexagons and pentagons. When first discovered in the 1980s, these tiny molecular cages seemed almost whimsical, but they opened a new chapter in nanotechnology. Each form of carbon, diamond, graphite, graphene, nanotube, fullerene, is like a verse in a poem about adaptability. That same flexibility may help carbon redeem its more troublesome side. For all its beauty, carbon is also the backbone of carbon dioxide, the greenhouse gas that traps heat in the atmosphere. Humanity has learned to pull carbon from the ground faster than the planet can reabsorb it, and the consequences are now reshaping climates and coastlines. Yet even here, chemistry offers hope. Instead of treating carbon dioxide as waste, researchers are learning to treat it as raw material, the foundation of a new carbon economy. Carbon capture and utilization, or CCU, aims to close the loop by turning emitted carbon dioxide back into useful compounds. Some methods pull it directly from smokestacks, others harvest it from the air itself. Once captured, it can be converted into fuels, plastics, or building materials using electricity, catalysts, and clever chemistry. Imagine a future where power plants not only stop polluting, but also become factories for construction materials, where every ton of carbon captured becomes a ton of value. One approach turns carbon dioxide into methanol or synthetic hydrocarbons, combining it with hydrogen produced from renewable energy. These fuels can power vehicles or aircraft without drawing new carbon from the ground. Another transforms carbon dioxide into carbonates, which can be mixed into concrete or used as feedstock for everyday products. Even biological systems are being enlisted. Algae and engineered microbes can feast on carbon dioxide, converting it into oils, proteins, or bioplastics. The idea is simple but profound, to turn the problem itself into part of the solution. The construction industry, one of the largest carbon emitters on Earth, is also undergoing a quiet revolution. Traditional cement production releases vast amounts of carbon dioxide, both from fuel use and from the chemistry of making lime. New formulations, however, absorb carbon dioxide during curing, locking it away in mineral form. This carbon-smart cement not only reduces emissions but actively reverses them. Meanwhile, biochar, charcoal produced from agricultural waste, can be mixed into soils or building materials to sequester carbon safely for centuries. Even steelmaking, once synonymous with smoke and fire, is turning green, using hydrogen instead of coal to strip oxygen from iron ore. The result is a cleaner, quieter kind of metallurgy, where carbon's role shifts from pollutant to partner. Carbon's versatility extends beyond industry to the polymers that surround us. Plastics, for all their convenience, have become one of the planet's most persistent challenges. Made mostly from fossil carbon, they degrade slowly and scatter across ecosystems. Scientists are now re-engineering these polymers to be recyclable or biodegradable, designing molecules that maintain performance but surrender gracefully to nature's processes when their time is up. Some use carbon captured from the air as a feedstock, turning atmospheric carbon into packaging, fibers, and films. Others incorporate chemical bonds that can be broken and reformed, creating a circular economy for plastics instead of a one-way ticket to landfill. Even energy itself is being reimagined through carbon. Synthetic hydrocarbons, fuels made from air, water, and renewable power, could one day replace fossil fuels entirely. By combining hydrogen from electrolysis with carbon dioxide captured from the atmosphere, scientists can produce gasoline, diesel, or jet fuel that burns cleanly and emits only as much carbon as it consumed during creation. The process is, in essence, a kind of artificial photosynthesis, a technological echo of what plants have been doing for hundreds of millions of years. These innovations don't erase carbon's darker chapters, but they rewrite them into something more hopeful. Humanity is learning to manage carbon as a cycle, rather than a one-way stream. Capture, reuse, rebuild, repeat. The key is to view it not as an enemy, but as an essential partner, one that can be guided toward balance through understanding and design. Carbon's story is far from over. It began in the cores of ancient stars where helium fused into heavier elements and was cast into space by supernovae. It settled on Earth, forming coal and diamond, limestone and leaf. It built the structures of every living thing, and now it writes the code of our digital lives, quite literally, since every piece of data we create depends on carbon-based chips, screens and storage. From the deepest mines to the atmosphere above, from black coal to brilliant diamond, carbon keeps reinventing itself. It can illuminate, pollute, or sustain, depending on how it's arranged and how we choose to use it. Perhaps that's why it feels almost human, adaptable, creative, occasionally troublesome, but endlessly capable of renewal. And so, the story of carbon continues, not as a tale of excess or depletion, but as one of transformation. From coal to diamond to data, carbon keeps reinventing itself, reminding us that even the most ancient elements can find new purpose when guided by imagination and care. Every element on the periodic table is capable of wonder and of trouble. Lead once brightened paint and softened pipes, mercury made mirrors shine, and cadmium lent vivid colour to early plastics. For much of history, chemistry's progress was judged by power, brightness, and performance. Only later did humanity realize that some of its cleverest inventions came with invisible costs: empoisoned water, polluted air, and damaged health. The 21st century is now rewriting the rules. The next chapter of chemistry is not just about what we can make, but how gently we can make it. This idea has a name: safer by design. Safer by design means thinking about hazard and sustainability from the start, not as afterthoughts, but as guiding principles. Every new material or reaction is evaluated not just for its effectiveness, but for its full life cycle, how it's made, how it behaves, and how it returns to the world once its job is done. The goal isn't to halt innovation, but to shape it, to ensure that progress no longer comes with side effects we only discover decades later. One of the most visible examples of this approach comes from colour itself. For centuries, artists and manufacturers relied on heavy metals to produce the rich pigments that defined eras of art and industry. Lead chromate gave us radiant yellows, cadmium sulfide produced intense reds and oranges, and cobalt oxide yielded brilliant blues. These colours were glorious, but also toxic, leaching into soil and water long after the paints dried. Today, the palette is being rewritten with safer alternatives: organic pigments, quantum dots, and engineered oxides that offer the same vibrancy without the lingering harm. Modern reds and blues owe their brilliance not to toxicity, but to precision, manipulating molecular structures so they absorb and reflect light exactly as desired. The same transition is unfolding in the world of energy. Batteries once relied on chemistries that, while effective, carried environmental baggage. Lead-acid batteries powered cars for over a century, but their manufacture and disposal required careful control to prevent contamination. Cadmium, once used in rechargeable nickel-cadmium batteries, is now largely phased out in favour of nickel metal hydride and lithium-ion technologies. Even those, however, are being reimagined. Researchers are developing sodium-ion, magnesium, and solid-state systems that rely on abundant non-toxic materials. Each advancement brings us closer to an energy landscape where power does not come at the expense of the planet's well-being. Electronics tell a similar story. The devices we depend on daily, phones, laptops, solar panels, are made from complex layers of metals and polymers, some of which can pose hazards if mishandled. The shift towards safer components means designing alternatives to toxic solders, flame retardants, and solvents. Lead-based solders, for instance, have been largely replaced by tin silver-copper alloys that perform just as well without spreading heavy metals through manufacturing waste streams. Circuit boards now incorporate halogen-free materials, reducing the release of corrosive gases in case of fire. It's an ongoing balancing act, maintaining reliability and miniaturization while cleaning up the hidden chemistry inside. Understanding what safe means, however, requires nuance. Every element has potential risks, but not all risks are equal. The key is distinguishing between hazard and risk. A hazard is an inherent property, toxicity, flammability, or persistence. Risk depends on exposure and dose. Even water in excess can be lethal. Even mercury in a sealed thermometer poses little danger. Safer by design doesn't aim to eliminate all hazards. That would be impossible. But to control them intelligently. It's about managing exposure, choosing substitutes wisely, and designing systems that prevent harm before it can occur. This philosophy has grown especially urgent with the realization that some chemicals never truly go away. PFAS, per- and polyfluoroalkyl substances, are a family of synthetic compounds prized for their resistance to heat, water, and grease. They're used in non-stick coatings, firefighting foams, and water-repellent fabrics. But their chemical stability, once seen as a virtue, has become their curse. They persist in the environment for centuries, accumulating in water, soil, and living organisms. Scientists now call them forever chemicals, a name that perfectly captures their stubbornness. Eliminating PFAS from industrial use has become a global priority. New materials, biodegradable coatings, ceramic barriers, and redesigned polymers are stepping in to replace them, proving that durability doesn't have to mean indestructibility. The challenge extends beyond molecules to the people who work with them. A truly safer periodic table protects not just consumers, but the workers and communities along every stage of production. Mining operations for rare metals can expose laborers to dust and toxins. Chemical plants may emit byproducts that drift into nearby neighborhoods. The principle of safer design calls for transparency, accountability, and fair treatment at every link in the chain. After all, a clean product built on unsafe labor practices is not truly sustainable. It's merely displaced harm. Some of the most thoughtful innovations come from small changes that ripple outward. In laboratories, replacing volatile solvents with water-based alternatives can drastically reduce inhalation risks. In manufacturing, switching from open processes to closed-loop systems prevents leaks and emissions. Even something as simple as rethinking packaging, eliminating unnecessary coatings, or using biodegradable polymers can transform an entire supply chain. Sustainability is rarely about a single invention. It's about the accumulation of small, deliberate choices. These choices require patience. A safer material might cost more to develop or perform slightly less efficiently at first. But as history shows, the long-term benefits — cleaner air, healthier workers, fewer environmental crises — more than outweigh the short-term trade-offs. Regulation and research often move hand in hand, each nudging the other forward. When governments ban hazardous substances, innovation accelerates to fill the gap. When scientists invent better options, policy evolves to support their adoption. The relationship between chemistry and ethics grows closer with each iteration, and sometimes progress reveals itself in quiet metrics. The air around a factory grows clearer, the groundwater beneath it runs cleaner. The workers no longer need respirators for routine tasks. These are the unseen triumphs of chemistry done right. The kind that won't make headlines but will define the next century. There's a deeper philosophy beneath it all. Chemistry, by nature, is a transformative science. It changes one thing into another, but the transformation we need most now is not just molecular, it's moral. It's the recognition that our greatest discoveries should not only enrich life but also preserve it. A new alloy, a new solvent, or a new polymer can change the world, but only if it does so kindly. Progress, after all, is measured not just in volts or speed or yield, but in how gently we achieve them. The periodic table is not just a list of possibilities, it's a responsibility. Each element offers a choice between power and restraint, between use and misuse. Designing the safer periodic table means learning to listen to the planet, to the people, and to the quiet chemistry that keeps everything alive. In that listening lies the future of science, not louder, faster, or brighter, but wiser. A future where the measure of success is not the complexity of our materials, but the care with which we make and manage them. Where chemistry's brilliance is matched by its conscience. Where progress hums softly, cleanly, and safely. A world in which even the smallest atom serves the greater harmony of life. Every human being is, in the most literal sense, a walking chemistry experiment. A living network of reactions sustained by the elements of the periodic table. Strip away the poetry, and you are roughly 2/3 oxygen by mass, built on a framework of carbon, held together by hydrogen and animated by nitrogen. But the quiet brilliance of life depends on more than these familiar building blocks. Scattered through every cell are trace elements, tiny quantities of metals and minerals that keep everything running smoothly. The body, it turns out, runs its own miniature chemistry lab. It just prefers to operate at room temperature and a steady heartbeat. Among the most vital of these trace elements is iron. Its role in biology borders on mythic. Every red blood cell carries millions of hemoglobin molecules, each containing 4 iron atoms at its core. These atoms bind oxygen in the lungs and release it where it's needed most, acting as couriers of breath itself. Without iron, oxygen would drift aimlessly through the bloodstream, unused and unclaimed. But as with any good catalyst, balance matters. Too little iron leads to anemia, a wearying lack of energy, while too much can damage tissues through oxidative stress. The body walks a delicate line, absorbing and storing just enough to sustain the flame without letting it flare. Zinc, another quiet hero, works behind the scenes in more than 300 enzymatic reactions. It helps repair DNA, heal wounds, and regulate the immune system. When you catch a cold and reach for a zinc lozenge, you're essentially giving your molecular machinery a small tune-up. Copper, by contrast, plays an electrical role, shuttling electrons through the enzymes that power cellular respiration. It's also crucial for forming connective tissue and maintaining the colour in your hair and skin. Iodine joins the ensemble as the guardian of metabolism, forming the hormones that regulate temperature, growth, and energy use. These elements, in trace amounts, keep the body's symphony in tune. Other elements make cameo appearances, equally vital though less celebrated. Selenium protects cells from oxidative damage. Magnesium steadies muscle contractions, including the heartbeat. Calcium strengthens bones but also triggers nerve impulses. Even elements like molybdenum and manganese have their moment, assisting enzymes that quietly detoxify and digest. Life is astonishingly democratic with its chemistry. A sprinkle of almost everything contributes to the whole. Medicine naturally has learned to speak this same elemental language. Many diagnostic tools and treatments rely on isotopes, versions of elements with slightly different atomic weights. In nuclear medicine, these isotopes act as tracers, revealing the inner workings of the body without invasive surgery. Technetium-99m, for example, is one of the most widely used medical isotopes in the world. When injected in tiny amounts, it travels to specific organs and emits gamma rays that can be detected by a scanner, painting a detailed picture of biological activity. Iodine-131 is used to monitor and treat thyroid disorders, while fluorine-18 helps power PET scans, illuminating how tissues metabolize glucose. Radioisotopes also play a role in therapy. Cobalt-60, once a workhorse of cancer treatment, delivers controlled radiation to destroy malignant cells while sparing healthy ones. Modern machines use more refined sources and focused beams, but the principle remains the same, using the precision of physics to guide the compassion of medicine. Even in its most intense form, radiation therapy is a dance of balance, enough energy to heal but not to harm. Some elements, however, go beyond diagnosis. They become medicines in their own right. In the 1970s, scientists discovered that platinum, the same metal that adorns jewelry and purifies car exhaust, could also treat cancer. The compound cisplatin binds to DNA inside cells, preventing replication and triggering cell death in rapidly dividing tumours. It became one of the most successful chemotherapy drugs ever developed. Later analogues like carboplatin and oxaliplatin refined the formula to reduce side effects and improve selectivity. Here, the same properties that make platinum a durable industrial catalyst also make it a biological one. A reminder that usefulness often transcends context. Gold, too, has a medical alter ego. Long used in dentistry for its stability and biocompatibility, it also forms the basis of some treatments for rheumatoid arthritis, where it modulates immune response. Researchers are now revisiting gold at the nanoscale, crafting particles only billionths of a meter across. These gold nanoparticles can absorb and scatter light in extraordinary ways, turning them into tools for targeted drug delivery or photothermal therapy, where tumours are gently heated and destroyed by focused light. Other metals lend their strength in more literal ways. Titanium, known for its combination of lightness and strength, has become the material of choice for implants and prosthetics. Its surface naturally forms a thin oxide layer that bonds seamlessly with bone, allowing the body to accept it almost as its own. Magnesium alloys, meanwhile, offer a remarkable twist. They can slowly dissolve inside the body, providing temporary support for healing bones or tissues before safely vanishing. The era of biocompatible materials is giving way to biocooperative ones, metals and alloys that don't just coexist with life, but actively work in rhythm with it. Silica and carbon join the story again through nanomedicine, a field that merges materials science with biology at the smallest scales. Silica nanoparticles can carry drugs directly to target sites, their surfaces engineered to recognize specific cell types. Lipid-coated nanocarriers, inspired by cell membranes, slip medicines through barriers once thought impermeable, like the blood-brain boundary. In some experimental systems, iron oxide nanoparticles act as tiny magnetic guides, steered by external fields to reach deep-seated tumours. It's a delicate choreography of elements, gold for delivery, iron for direction, silicon for structure, all working together inside the most complex laboratory ever built, the human body. Even calcium, long associated with bones and teeth, has taken on new medical roles. Calcium-based scaffolds help regenerate tissues, calcium phosphate coatings improve implant stability, and in cellular signaling, calcium acts as a messenger, pulsing like a microscopic telegraph across membranes. Meanwhile, trace elements once considered incidental are revealing unexpected importance. Vanadium in blood sugar regulation, chromium in metabolism, lithium in mood stabilization. The periodic table, it seems, is a medicine cabinet we're only beginning to organize. For all its sophistication, though, the body's chemistry remains humble in principle. It operates at modest temperatures, neutral pH, and under the soft pressure of everyday life. Every heartbeat, every breath, every thought arises from molecular exchanges that obey the same physical laws as the reactions in a laboratory. The only difference is scale and grace. That humility offers a quiet lesson. In an age of complex pharmaceuticals and advanced biotechnology, the foundation of health still lies in balance. Enough iron, but not too much. Sufficient iodine without excess. Trace copper, zinc, and selenium in careful proportion. The same laws that govern stars and circuits also govern a living cell, only slow to a peaceful rhythm that allows consciousness to emerge. Perhaps that's the most extraordinary realization of all. The periodic table doesn't stop at the laboratory wall. It extends into the bloodstream, the bones, the brain. Its elements shape our structures, fuel our reactions, and repair our mistakes. The same gold that decorates a ring can deliver medicine. The same carbon that builds skyscrapers forms the lattice of life. Even the body runs a tiny chemistry lab. It just prefers body temperature. And when it works well, it reminds us of something profound, that life itself is not separate from matter, but the most elegant arrangement of it. The same periodic table that builds engines and cities also keeps your heartbeat steady. Proof that the universe's simplest ingredients can sustain its most complex creation. When humanity dreams of building beyond Earth, the imagination tends to leap straight to rockets, domes, and gleaming bases under alien skies. But once the first explorers arrive, the real challenge will be far less glamorous. Where to find bricks, air, and batteries? Carrying everything from Earth would be like trying to camp for years while bringing along every grain of sand and every breath of air. So, the future of space settlement depends on one elegant idea: in situ resource utilization, or ISRU. In plain terms, it means using what's already there. Instead of importing steel, fuel, and oxygen at astronomical cost, astronauts could mine, refine, and build using the materials of the Moon, Mars, or even asteroids. It's the difference between surviving off a supply ship and becoming self-sufficient. The technology is still developing, but the principle is ancient. Wherever life goes, it learns to use the land, even when that land happens to be made of dust, rock, and cosmic radiation. Take the Moon, for instance. It may look barren, but its surface, as the fine grey powder called regolith, is surprisingly rich in potential. Lunar regolith is made up of crushed basalt, glassy fragments, and minerals such as ilmenite, a titanium iron oxide. Hidden within that mineral mix is oxygen, not as gas, but locked into oxides and silicates. If extracted, that oxygen could fill habitats, fuel rockets, or even support industry. Since oxygen accounts for nearly half the mass of lunar soil, it's less about whether it's there and more about how gently we can free it. One promising technique involves molten salt electrolysis, where regolith is heated until it melts, and an electric current pulls oxygen atoms free, leaving behind useful metals like iron and titanium. Another uses hydrogen to react with ilmenite, producing water that can later be split into oxygen and hydrogen again. The byproducts, metal powders and ceramic-like residue, can serve as raw material for construction, 3D printing, or shielding against radiation. It's chemistry turned into architecture. Building on the moon won't mean mixing cement in zero atmosphere. Instead, structures might be sintered directly from regolith. That is, melted and fused into solid blocks using focused sunlight or microwave heating. Experiments on Earth have already shown that lunar dust simulants can be shaped into strong bricks using only heat and pressure. Even the moon's fine dust, so notorious for clinging to everything, could one day be an asset, forming glassy coatings or insulating layers. In a sense, the moon itself could become the quarry, foundry, and workshop for future explorers. Mars offers a richer but trickier chemical playground. Its thin atmosphere is mostly carbon dioxide, over 95% of it, and its surface contains perchlorates, iron oxides, and frozen water. Each ingredient presents both challenge and opportunity. Carbon dioxide, for example, can be split into oxygen and carbon monoxide using electrolysis powered by solar or nuclear energy. The Mars Oxygen ISRU experiment, or MOXIE, aboard NASA's Perseverance rover, has already demonstrated this in miniature, producing measurable oxygen directly from the Martian air. Perchlorates, while toxic to humans, could serve as oxidizers for rocket propellants, or be broken down for useful oxygen. The iron-rich soil gives Mars its iconic red hue, and could, with enough energy, be smelted into building materials. And beneath the dust, radar and probes have confirmed the presence of water ice in vast quantities, especially near the poles. Water is the ultimate resource, drinkable, breathable, when split into hydrogen and oxygen, and indispensable for growing food. The challenge lies in reaching it, extracting ice from permafrost in sub-zero conditions without losing it to the thin, eager atmosphere above. If the moon's biggest resource problem is abundance without accessibility, Mars's is accessibility tangled with chemistry. These same compounds that offer promise can also corrode, contaminate, or complicate machinery. Perchlorates, for instance, are reactive and cling stubbornly to surfaces, while Martian dust is electrostatically charged and can grind seals and joints to ruin. Engineers designing habitats and rovers must think not only about what materials can be made there, but how long they'll survive the grit. Energy, as always, ties everything together. On both the Moon and Mars, solar power will likely be the first line of supply. Sunlight is abundant, but the details differ dramatically. The Moon's day lasts about 2 Earth weeks, followed by 2 weeks of night, a rhythm that demands robust storage systems. Batteries, fuel cells, or thermal energy stored in molten salts could bridge those long dark stretches. Mars, meanwhile, receives only about half the solar energy Earth does, and dust storms can dim the sky for weeks. To supplement solar power, small fission reactors are being developed, compact, reliable sources of heat and electricity that can hum quietly through long Martian winters. Low gravity itself introduces new challenges and opportunities for energy systems. Liquids and gases behave differently when buoyancy and convection weaken. Cooling becomes harder. Fuels may stratify or bubble unpredictably. Yet low gravity also makes construction and lifting easier. A single robotic crane could move multi-ton slabs of regolith into place with minimal energy, and launching materials into orbit becomes dramatically cheaper than from Earth. The same physics that hinders heat flow might make manufacturing more efficient, allowing metals and ceramics to settle into perfect crystal forms undisturbed by turbulence. The harsh environment will demand materials that can withstand constant assault from dust, radiation, and extreme temperature swings. Lunar dust is sharp, almost glassy, having never been weathered by wind or rain. Martian dust, fine and pervasive, contains perfluorates that can corrode metals and degrade plastics. Engineers are experimenting with coatings that repel dust using static charge or textured surfaces that prevent adhesion. Other concepts involve self-healing materials, polymers that reknit microscopic cracks, ceramics that refuse under heat, and composites that shrug off repeated radiation exposure. Ultimately, designing for alien worlds is an exercise in humility. Every gram counts, every molecule matters, and nothing can be wasted. The principles of sustainability that seem urgent on Earth, recycling, efficiency, minimalism, become non-negotiable in space. A lunar base will likely recycle every drop of water, every whiff of air, and every scrap of material. Waste will become feedstock. Yesterday's carbon dioxide might become tomorrow's rocket fuel. The circular economy that feels idealistic on Earth will be mandatory beyond it. Even more than technology, this approach represents a shift in mindset. The dream of living off-world often carries echoes of escape, a new beginning somewhere untouched. But the truth is the opposite. Building wisely on the Moon or Mars begins with mastering sustainability here on Earth. The lessons we learn in conserving, recycling, and refining will follow us wherever we go. A fragile planet taught us how to live with limits. The cosmos will test how well we learned. Perhaps that's the quiet poetry of in situ resource utilization. It's not just about digging oxygen from rock or fuel from air. It's about respect for material itself. On other worlds, the smallest speck of dust or the faintest trickle of water might mean survival. In learning to build there, we might rediscover gratitude for what we already have here. The first bricks on another world may not gleam like marble, but they will carry a profound meaning. They will mark the moment humanity learned that sustainability isn't a constraint. It's the art of thriving with grace. Whether on the red plains of Mars or the silver deserts of the Moon, every structure we raise will echo that same lesson, that our future among the stars depends, more than anything else, on how carefully we treat the matter beneath our feet. Every age of science has its triumphs and its shadows. The Stone Age gave us tools and trade. The Iron Age brought empires and warfare. The Silicon Age has given us instant connection and invisible dependence. For every gleaming device or breakthrough alloy, there are unseen hands that mined, refined, and assembled it. The modern world is in many ways built on elements, but the story of how we use them is as important as what we build with them. The chemistry of progress now needs a new discipline, the ethics of matter. When we speak of innovation, it's tempting to picture laboratories, discoveries, and equations. Yet every material, from the lithium in a battery to the cobalt in an electric car, carries a social footprint as real as its chemical one. The question then is not just what the element can do, but who benefits from its brilliance and who bears the cost. Consider the global web that powers a single smartphone. Its supply chain stretches across continents. Lithium from South American brines, cobalt from Central Africa, nickel and rare earths from mines in Asia and Australia. Each step transforms raw minerals into polished technology, but along the way, workers may face poor conditions, water sources may be strained, and communities may see their landscapes altered beyond recognition. The ethical challenge is clear. How do we make progress that shines without leaving shadows behind it? Fair sourcing is becoming the quiet revolution of materials science. It's about tracing the origin of every atom with the same precision we trace its behavior in the lab. Technologies like blockchain and isotopic fingerprinting can track metals from mine to market, ensuring transparency. Certification programs now recognize responsibly sourced minerals, just as fair trade labels once transformed agriculture. Companies are beginning to understand that sustainability is not just about carbon, it's about conscience. Recycling too plays a moral role. Much of the world's electronic waste still ends up in informal recycling centres, where workers dismantle devices by hand, often without safety equipment. The same metals that once symbolized modernity become hazards when handled without care. A truly ethical material cycle must protect both the planet and the people who keep that cycle turning. Clean, automated recycling plants, fair wages, and access to training can turn what was once a source of harm into a source of dignity and livelihood. Ethics also extends to design. The choice of materials in a product, whether it uses conflict-free metals, recyclable polymers, or easily replaceable components, determines its afterlife long before it reaches the consumer. Engineers now speak of design for disassembly, creating products that can be repaired, upgraded, or recycled instead of discarded. This philosophy treats every object as temporary, part of a larger flow of matter rather than a terminal point. It's chemistry with empathy built in. And empathy, as it turns out, may be one of the most universal elements of all. Even ethics has its own periodic table, mostly composed of empathy. Education is the next essential ingredient. The skills that once defined industry, forging, welding, smelting, are being joined by new crafts, materials engineering, nanofabrication, electrochemistry. As technology evolves, so must access to it. A sustainable and ethical world depends on inclusivity, on training not just the privileged few, but communities everywhere to take part in this new material economy. Imagine a global classroom where a student in Kenya can learn to 3D print solar cells, or a technician in Peru can help refine battery materials using local minerals. Knowledge, shared fairly, becomes the purest element of all, one that multiplies rather than depletes. Education also carries cultural weight. Many indigenous communities have long practiced forms of stewardship that echo today's sustainability principles, using local materials wisely, minimizing waste, and respecting natural cycles. Their traditions remind us that innovation doesn't always mean invention. Sometimes it means remembering. By combining ancient knowledge with modern science, humanity can rediscover a more balanced approach to material progress, one that values continuity as much as change. Global resilience depends on this diversity of ideas as much as on diversity of materials. The pandemic, supply disruptions, and geopolitical tensions have shown how fragile our material networks can be. A shortage of one element in one region can ripple through entire economies. Building resilience means spreading risk, finding alternative sources, recycling critical materials, and developing substitutes where possible. It also means embracing circular economies, where waste from one process becomes feedstock for another. When a solar panel at the end of its life provides raw silicon for new ones, or when used batteries yield lithium for the next generation, we move closer to a self-sustaining material world. These systems work best when shared globally, not hoarded. The future of matter should not be a contest for control, but a collaboration for continuity. Open research, fair trade, and cooperative standards can ensure that every nation benefits from the elemental revolution. Chemistry, after all, doesn't recognize borders. Oxygen and hydrogen mix freely, and so should ideas. There's also an emotional truth here, one that often hides beneath the equations and technical reports. Every new discovery, every cleaner process or lighter alloy is an act of trust in the future. The scientists and engineers designing safer batteries, recyclable plastics and efficient solar cells are not only solving technical puzzles, they are expressing faith that their work will be used wisely. The moral responsibility lies not only with the inventors, but with everyone who benefits: consumers, policymakers, educators, and communities alike. The calm shape of progress is not a race or a conquest. It's a conversation between curiosity and care. Innovation without ethics can accelerate us toward imbalance. Ethics without innovation can leave us standing still. The art lies in harmonizing the two, allowing science to move forward with humility. The next breakthroughs may come not from discovering new elements, but from rediscovering values: cooperation, compassion, foresight. In the same way that chemists once learned to combine atoms for strength, humanity must learn to combine intentions for fairness. Perhaps in the end, the measure of a civilization is not how many elements it has mastered, but how wisely it uses them. A battery that powers a hospital in one country should not depend on suffering in another. A smartphone that connects people should not disconnect them from the consequences of its creation. Progress must be judged not only by performance, but by kindness, not by how much we extract, but by how much we give back. There is something poetic in imagining a future where technology hums quietly, supply chains are transparent, and every product tells the truth of its making, where children study chemistry not just to manipulate matter but to respect it, where ethics and science finally stop being separate subjects and start sharing the same laboratory bench. Because the future of elements is not just what we build, it's how kindly we build it. And perhaps that is the gentlest kind of progress, one that glows softly, not from the brilliance of its metals or the power of its machines, but from the steady light of responsibility shining through it all. From the first spark of a star to the quiet hum of a laboratory, the story of the elements has always been one of transformation, not of themselves, but of us. The same atoms that once drifted through the vastness of interstellar space now sit in circuits, bones, oceans, and art. The hydrogen forged in the universe's first few minutes still burns in our stars and in our cells. The iron born in supernovae runs in our blood. We are quite literally recycled stardust, only rearranged into new shapes, guided by curiosity and care. What has changed over billions of years is not the material itself, but the mind that shapes it. Elements do not evolve in character, they simply wait for context. Carbon doesn't know it has become the backbone of DNA, and oxygen doesn't realize it keeps both stars and lungs alive. It is our awareness, the choices we make, that turn chemistry into civilization. The atoms remain the same, the intentions that arrange them do not. The arc of this story has stretched from stellar furnaces to sustainable futures. It began with hydrogen fusing into helium, building the first scaffolds of matter, and it continues now with humanity learning to rebuild the world responsibly from what those stars left behind. Every discovery we make, from the shimmering sheet of graphene to the humble recycling bin, is part of that same continuum. There is no boundary between cosmic and human chemistry, only a change in tempo. The dance that once played out in the heart of suns now plays out beneath the soft glow of desk lamps and data screens. Chemistry, at its heart, is choreography between matter and mind. Every reaction we design, every element we refine, is a step in that delicate rhythm. It's easy to think of progress as loud, explosions, launches, inventions, but the deepest transformations often whisper. A new catalyst that saves energy, a gentler solvent that spares a river, an alloy that lasts decades longer than its predecessor. These are the quiet revolutions, the ones that let humanity grow without breaking what sustains it. Across the ages, the periodic table has become both a map and a mirror. It shows us the structure of reality, but it also reflects our values. When we first arranged it, we saw order where there had been chaos. Now we see responsibility where there was once only potential. The future of chemistry will not be measured by how many new elements we discover, but by how harmoniously we live with the ones we already know. Even humour finds its place in that reflection. The universe may not check its watch, but it keeps excellent attendance, showing up every second in every atom perfectly on time. We meanwhile are the latecomers, still learning to listen to the rhythm of the cosmos. It is humbling to realize that everything we create, from medicine to spacecraft, is, at the deepest level, a rearrangement of what already exists. The oxygen we breathe, the silicon that carries our thoughts, the gold that gleams in circuits, all of it once drifted through stellar winds. Nothing new is truly made, it is only borrowed, reshaped, and returned. Progress, then, is not the invention of matter, but the refinement of meaning. And meaning, like chemistry, is cyclical. Each generation inherits a table of possibilities and adds new notes to its margins. Safer materials, cleaner processes, wiser uses. The great challenge of our time is not discovering more elements, but deserving the ones we have, to use them with restraint, to recycle them with respect, and to let wonder guide their use more than greed ever could. As we look to the stars for inspiration, and perhaps one day for habitation, the lesson remains the same. Sustainability is not a frontier, but a practice. The Moon and Mars may hold new elements for our ambition, but they will also test the same question that Earth has always asked us. Can we build without breaking? Can we learn to see matter as a companion, not just a resource? The beauty of chemistry lies in its patience. Atoms wait billions of years for the right conditions to form a molecule, and molecules wait eons more to become life. We too are part of that patience, a species learning to slow down, to understand before we act. The more we study the elements, the more we realize how ancient they are, and how young our stewardship remains. So tonight, as we close this exploration of the elemental future, there's comfort in knowing that the story continues, not just in laboratories or stars, but in every object and breath around us. Time and matter share a secret. They never really stop. The same carbon that warms a fire may one day form a mountain. The same iron that built a city may someday drift again among the stars. May your next hour pass gently, and your next discovery rest quietly in starlight.